Hello and welcome everyone to Mount San Antonio College, Weld 40. And during this lecture, I'm going to talk to you about MIG welding and also flux cored arc welding, both the processes. So we begin those processes in week 11 and we do the other process in week 12. But I wanted to cover both processes because some of you are going to be doing some MIG welding in week 11 and some will be doing flux cored arc welding. So I wanted to talk about both subjects at this time. The formal name for this process is gas metal arc welding, GMAW. When it initially started, the term MIG was used, which stands for metal inert gas. These inert gases that they were using were helium and argon. But because the industry changed and obviously different types of metals and alloyed metals, sometimes the gases were no longer inert. So they were using carbon dioxide, they were using oxygen, and so they had to change the name of the welding process. So they changed it to gas metal arc welding, which is the formal name. If you have any welding procedures, you'll actually see it printed that way, gas metal arc welding. But whether I say gas metal arc welding or whether I say MIG, I'm talking about the same process, which is in essence a solid wire coming out of the end of a gun handle of a contact tip, but it's a solid wire coming out the end that feeds onto the weld metal itself so you can produce the weld. So again, continuous feed of bare wire. It was developed in 1948. From the welding machine itself, there'll be a lead that goes to the gun handle that the welder actually holds. This lead has a liner in it, and the solid wire is fed through that liner all the way to the gun handle, and then of course it comes out through this contact tip to do the welding. The liners are typically made out of either Teflon or nylon, or they have a coiled wire in them. And I should say at this time, if the wire ever gets like gummed up or it's not feeding properly, you just put a new spool on it, it just doesn't seem like it's feeding well. You may have had a buildup in these liners. So it wasn't uncommon for us on a side of a building. Welders would disconnect the leads from the welding machine itself, and they would spray WD-40 in there and get any kind of oils or anything that would build up in the liner itself so that the wires could feed easily. The other option, of course, is just buy a new liner. The only thing is these liners, they're not interchangeable between the different manufacturers of Miller, Lincoln, Hobart, or whatever. They're not interchangeable between the machines, but that's certainly a viable alternative. And I know people that once the wires, it starts getting caught and such and so forth, that wire sometimes it gets turned in the lead, so the wire's got to go around a turn, and sometimes going around that turn, obviously multitudes of times, it starts wearing away at these liners. So if any of that happens, you may have to purchase a new liner from the machine itself to the gun handle. With this process, I'd like to talk to you about what kind of metals typically get welded. I'll bring this, I got kind of a podium here. Mild steel, stainless steel, nickel, Manel, which is a copper nickel, Inconel, aluminum, magnesium, titanium, silicon bronze, deoxidized copper. So you can see that there's a number of different types of metals that you can MIG weld with. You can certainly weld a variety of metals very fast. It's easy to handle. It's got a high deposition rate. It's a neat process. And during World War II, we found out that TIG welding was used quite well with the thinner metals. They wanted something for a little bit thicker metals, and that was the start of this. You can see that it was started right after World War II. So what can you weld with it nowadays? Well, you can certainly weld light metals. Um, with the lighter wires, 030, 035 wires, um, you can weld very, very thin metals and dial the machine in so that it can weld those light gauge metals. You can also weld heavy metals with it, and we're talking about 900 to 1,000 amps. So you can imagine over the last few weeks here, you all have been using 125 amps. Imagine 1,000 amps, and the actual solid wire size is 1/8 inch in diameter or 532. So it's just a coil of 1/8 inch diameter wire being fed, and that's quite a bit of welding going on at 140 inches per minute. Now, that's a possibility. All I wanted to tell you is that mostly in the industry nowadays, it's used for the lighter gauge metals. This heavier gauge type of welding, normally flux cored arc welding is used, and I'll be talking about that in just a moment. Because it's a continuous feed of bare wire, it's important to note that you've got to have a backing gas with this. If you don't have a backing gas with it, the nitrogen and the oxygen in the air will contaminate the mold puddle. So as you know, our breathing atmosphere is 78% nitrogen and 21% oxygen. Those nitrides and oxides, they want to attack a molten puddle. And so this backing gas that's used for the MIG welding, it's typically 75% argon, 25% CO2. It comes in a cylinder. You would connect it to the welding machine itself. And in essence, the way that it works is let me get a designation here for it. The way it works is in the gun handle itself. When you activate the trigger in the gun handle itself, it opens up a solenoid, and the gas flows from the cylinder itself, flows through a gas hose through the lead to the gun end. So it displaces the breathing atmosphere and provides an acceptable atmosphere in order for you to produce the welding, so that it doesn't become contaminated. The very common backing gas that's used is 75% argon, 25% CO2, or very commonly used called steel mix. So if you ever go to a welding store and you want to get a cylinder filled for your MIG welding, just tell them you want a steel mix and they'll give you this setup. Again, this is the most common one that's used. That doesn't mean you can't use other types of backing gases. I'm just saying that the bulk of the work is used with this with mild steel. When you get into the stainless steels and the aluminums, those you would use an argon backing gas. But I can tell you, I've used this process quite a bit. It's very easy to use. Certainly user-friendly when you're dealing with thinner gauge metals. This backing gas is also going to have a regulator. So on the cylinder itself, there's going to be a regulator there. And so I'll try to kind of I'll just draw in a regulator here to use. But coming out of the regulator, there's going to be a glass tube. And there's going to be increments on the glass tube. And you're going to want to read the top of the ball. Now, I tried to draw a ball in here. That's my artistic deal. But when you open this up, the ball is going to kind of float in here. And you're going to want to raise the ball up. And again, read the top of the ball and bring it up to 20 CFH, 20 cubic feet per hour. And so that when you activate the trigger in the gun handle, it opens up a solenoid that allows the gas to flow, and then you can proceed and go ahead and do this welding process. It's very common in the gun handle itself. There's a nozzle, and I'll do my best to try to draw this, but here will be the gun handle itself. Coming off of that, there's going to be a contact tip, and then there's going to be a nozzle that goes beyond that. And in this nozzle here, it's not uncommon to use an anti-splatter spray. It looks like a paint can, but they just kind of spray it inside the nozzle itself so that any of the splatter from the MIG process doesn't get all caught up into the nozzle itself. The other important item to keep in mind here is that this process is considered semi-automatic, meaning that as soon as I activate the trigger mechanism, the wire starts to feed and it opens up the solenoid that allows the gas to feed. It's semi-automatic. And with that, we have to have constant voltage. And I know this is unfair, it's just a term, kind of said to you verbally, but I'm going to do my best to try to explain it to you. Almost any welding machine that you buy is going to be constant current, meaning that the current is going to stay steady. When you get into these semi-automatic processes, namely MIG welding and flux cored arc welding, you have to have constant voltage. And what that is that during the welding process, the voltage does not fluctuate. It doesn't go up or down and such and so forth because the wire won't work properly. Now, you can buy welding machines that they literally have a switch. It'll say sheet metal arc welding, and then you just move the switch over and it says gas metal arc welding or flux cored arc welding. And that's your constant voltage right there. And then you can hook up your MIG machine and go ahead and produce your welding. Some of the older machines, they don't have those switches. So you pay for those, right? That it's a little bit more money to pay for that in the welding machine itself. You can also buy a constant voltage converter that goes into the side of the machine. It actually bolts into the side of the machine, and it's hooked up electronically. And then you just take the leads from the machine from sheet metal arc welding, and you just hook it up to the constant voltage hookup to the converter. And then now that will allow you to do the MIG welding or the flux core arc welding. To give you an example, I got called to a project. There was a welder struggling with some MIG aluminum on a project, and it looked kind of like bubble gum, and there was some porosity in the weld. And I followed the lead back to the welding machine, and I saw that the welding machine was not constant voltage. There was no converter on the switches itself on the face of the machine. I went and got the superintendent at the job site, and I said, "You've got an issue here. This person's trying to MIG weld with constant current, which is non-certified, and you guys got to get a machine out here that can weld this properly." So he brought me back to the machine, and he opened up the side of the machine, and right there was the constant voltage converter. So they had a converter on the machine already hooked up. It just wasn't being used properly. So we unhooked it up, hooked it into the converter, and then of course the welding proceeded very, very well. I made a very good friend that day. The welder was really struggling, and we got it working for him, and everything worked just fine. Now that was a number of years ago. Nowadays, the cost of these machines having the dual purpose of sheet metal arc welding and MIG or flux cored arc welding with this constant voltage, they become more affordable, if you will, as far as the pocketbook from what they were in the earlier days. I just wanted you to know that if you had an older machine, you could buy a constant voltage converter and hook it up if you wanted to run these semi-automatic wires. A couple concepts to talk to you about with MIG welding. One is that the hard wires, like mild steel, those wires are pushed from the machine. They actually have a driving mechanism with spindles, and they push it from the machine through the lead all the way to the gun handle itself. So those are the harder wires, and they're fed from the machine. The softer wires, like aluminum, those are pulled at the gun handle itself. So that the gun handles for aluminum, they're actually wider because the spindles that move, that pull these softer wires. They're pulled right at the handle, a little bit wider, and that's how the softer wires are MIG welded. That concept. The other concept is that with this welding process, you can either push weld or you can backhand weld. Either way. So in other words, I can activate it and actually push weld in this direction, or I can back weld in this direction, where I literally have to look through the nozzle and the gooseneck, if you will. I'd have to look through that as I'm doing the welding. Either way, it works just fine. I typically like to push weld because I get the visual. You can see it very, very easily as you're doing the weld. One of the old timers that showed me he oscillated it. So I caught on that. I liked that process. It kind of helped me with my timing. So you'll see me to this day that when I MIG weld, I always do an oscillation. I like the texture to it, I like the look to it, but it also helps me with my timing as I'm doing the weld itself. So it's a high deposit rate. There's no flux and there's no slag. So let's talk about some of the advantages. Some of the advantages, well, the arc is very visible to the welder. That's a big, that's a plus. And you can weld in all positions. There's no slag, there's no splatter. You can literally paint right over the weld. You can do a weld and just send it to the paint shop, and with minor work, they can go ahead and start with the painting process. So no flux to clean up. There's less distortion. So you'll find that you can weld these light gauge metals and the metal doesn't warp. It's a very, very quick weld to do. And that's an advantage with the welding. You can also weld poor fit-ups. So, I mean, you can literally dial in the voltage and the amperage where you can have a gap between the two metals. And you can just bridge right across it, just weld right across it. It's a really, really neat process to use. And once the voltage and the amperage is dialed in, makes it much easier to work with. Okay, so the last thing I wanted to talk to you about with the MIG welding are these two items here, the amperage and the voltage. The amperage is the wire speed, and the voltage is the heat. So the way this works is if you're doing a weld and your weld is just sitting on top, it's not fused in real well, you're going to have to increase the voltage or the heat in order to get this to flatten out. That's how it works. These two are copacetic with one another. Usually when you adjust one, you're going to have to adjust the other. But the term amps is wire speed. So in the old MIG machines, what you're going to see is you're going to see the term amps and voltage. That's it. You'll only see amps and voltage. On the newer machines, you're going to see the words wire speed written, and then you'll also see the word voltage. But you need to know as a welder that when you're adjusting the voltage, you're adjusting the heat. And when you're adjusting the wire speed, you're adjusting the amperage. When you get these two dialed in properly, it sounds like bacon frying, is what it sounds like. You're not over penetrating. Let me give you some of the signs of it, okay? Voltage, I just demonstrated to you. If it's real cold, you're going to have to increase the voltage. Again, if you're burning through the material, you're going to have to back off on the voltage because you have too much heat in order to get the right penetration value with it. On the wire speed, if the gun itself, the weld gun itself, if it's kicking back at you, your wire speed is too fast. You need to turn down the wire speed so that it moves smoothly. If your wire speed is too slow, it will actually burn itself right back into this contact tip, right in this area. It'll actually burn and do some damage to the contact tip. So that's one of the signs of it being too slow of a wire speed. But there's a balance between these two. Once you get it dialed in, usually you have a scrap piece of material and you work at it. Once it's working properly, it's really, really easy to work with. Some of the newer machines that you buy, electronically, right on the machine itself, it already sets itself. In other words, you would have 1/8 inch material, 0.125, and it already has the volts and amperage already set because you've already preset them in the machine. So you can go to 1/8 inch material, 3/16 material, 1/4 inch material, 1/2 inch material, and whatever you've preset the machine to that has worked on those thicknesses, the machine will automatically set itself to it. It's just that I wanted to talk to you about the concept that of voltage meaning the heat and amperage being the wire speed. Those are the two adjustments on the machine for the weld to be done properly. So with that, I think that kind of talks about everything that I wanted to say about MIG welding or gas metal arc welding, that process. And we'll go ahead and move to flux cored arc welding. So with the flux cored arc welding, I mean, very commonly, right? We weld mild steel with it. You can weld stainless steels with it, the high nickel alloys, and you can do some hard surfacing. This process has taken over the welding industry quite a bit over the last 10 years or so because you can weld both light gauge metals with it, thin metals, and you can also weld the heavier gauge metals. I mean, it's very common. If you're driving down the street and you see a building going up with columns and beams and stuff like that, more than likely they're flux core arc welding the building together. And the only welder that I have, I purchased, I have a 140C. That's what I have, Lincoln 140C. Works very, very well electronically, but I just plug it into a 110 outlet. These machines that are MIG flux cord, that Miller sells, Lincoln sells, and so forth, any of the other suppliers, you can buy them just 110 machines, or you can buy them also 110 volt or 220 also. So it's fairly easy to convert them from 110 to 220, and also you would get a higher duty cycle with the machine if you use 220 with it. So if you have 220 in your garage, that might be a nice investment for you. I think right now while I'm talking to you, the Miller, those go for around $1,100–1,200 for the 110, 220 machines. The one that I bought, I think I paid $760 for it. Unfortunately, right after I bought it, I saw it in a penny saver where someone had bought it and tried to get rid of it, and it had a cart with it also for $350. So I'm just saying that only because that might help you with your decisions on what you do. But this machine that I have has worked for quite a while, over a number of years. I already talked to you all that I had it up about 5 feet in the air and actually fell over and hit concrete, and it kept right on going. So I still have it to this day. Here we are 5 years later, and it's working quite well. The flux core arc welding puts out a very high quality weld. It's a lower cost than sheet metal arc welding. Let me talk to you about how it works. The flux is in the center of the wire. Interesting concept. So in other words, it's a very thin piece of flat stock wire, if you will, and it goes into a die, and then the die slightly curves it, and then it goes into another die and it slightly curves it a little bit more, and then there's a hopper there that drops the granulars into the center of the wire, and then the next die pinches it over, and the next die pinches it completely closed, if you will. So that the flux is actually in the center of the wire. We used to call it like an inverted 70-18 electrode. Rather than having the flux on the outside of the electrode, it's on the inside of the wire. The interesting concept on that is that as it exits out because there'll be a nozzle here and there'll be a contact tip. As it exits out the contact tip, you can break it right here just with your fingers. Just take your fingers and break the wire off. It's very easy to do because the flux is in the center of the wire itself. I kind of tried to drew it here. So the wires are 030 to 1/8 inch in diameter. This process we use DC minus polarity for the flux core arc welding. With this you use 24% less flux. So on your typical 70-18 electrode, it's got a binder in it to hold the flux onto the bare wire, if you will. But to hold the flux onto the electrode, it uses a binder. And there's no binders needed. So you end up using 24% less flux than you would with shield metal arc welding. Also, I need to tell you that you can use this flux in the center of the wire only, or you can use a dual shield. Now you can also have a backing gas, much like MIG welding when I was talking about it earlier, where they would use like CO2, carbon dioxide, or argon as a backing gas. We call that dual shield welding. But typically that's only used if the welding procedure calls for that. WPS stands for Welding Procedure Specification. So only if the welding procedure called for a dual shield, that's where you would use it. You know, I got almost 40 years of welding, 38 years. But in all my years of the welding, I've only used this once with the dual shield. So everything else that I've been around, or any of the welders that I've been around, I've always just used just the flux only in the center of the wire for this welding process. So it was developed in 1954, if I didn't mention that, certainly right after the MIG welding was established. And it's gained a stronghold in the industry itself. The designation on the wire, this is a very, very common designation, E70T-4. That T stands for tubular, because the flux is in the center of the wire. They call it tubular. So whenever you see that T, note that stands for tubular, and you're talking about flux core arc welding. If this was an S, that would indicate solid, meaning that you're doing the MIG welding, which was the previous process that we were talking about. I actually had this on a test, and I didn't know what it was. I hadn't been told what the answer was. So I always cover this in my lecture. Know that the S stands for solid, and that's MIG welding, and the T stands for tubular, which is for flux core arc welding. This process, again, it's also semi-automatic. It uses the constant voltage just like the MIG welding does. So you'll have to have constant voltage when you're using this welding process. So, okay, what are the positives? You have very good deposition rates with it, very good metallurgical values, very good visibility during the welding. You can weld thin and definitely thick materials with this. You can weld in all positions. All the filler metal is consumed. That's an interesting concept, because all of the wire itself is consumed. There's no waste, as you would with stick welding, if you will, where you have the stubs where you're throwing those away. So there's very little waste. You do want to remove any rust or scale or oil or grease on the metal before you do any of this welding. But the last concept I wanted to tell you about and it's really important, is it's called stick out. And I'll try to rewrite this so it's kind of a clear concept. But with flux core arc welding, when the wire comes out of the nozzle, this is called a nozzle, right here. There's a contact tip right here that's made out of copper, and the flux core wire feeds through it. When it comes out of the nozzle right here, we usually get a minimum of a 1/2 inch stick out coming out of the nozzle. So in other words, let me compare it. With the MIG welding, you can get as close as you want. You can bring the nozzle right up and bring the wire right up with it. But with this process, if you bring that nozzle any closer to within a 1/2 inch, it will actually fry this contact tip inside the nozzle itself. So you can go through quite a few bit of contact tips very quickly if you're not real careful with it. Some of the wires require 3/4 stick out. Some of them are 1 inch stick out. So you literally have to have a wire. So what it's saying is that during the welding process, you do not want to be any closer to the weld metal itself than 1/2 inch during this process. Is a good rule of thumb to go by, so you're not damaging this contact tip. And I think that's about it. That's kind of what I wanted to talk about. These are both very, very neat processes to use. There's a reason why you would use one other than the other. And that comes from actually doing the process itself and seeing what it can do and the versatility of it. I think that's it. Thanks, everyone.